So starting with HC Verma question number 7. Okay. So you have to find the amount of force you need to apply to an object lying on a rough inclined plane of given inclination and given coefficient of friction. So in this particular question, the angle of inclination is 30 degrees. Okay. And the coefficient of friction is 0.2. So if you have an object placed over here, as you know, what is happening is because mu is less than tan theta, so it will tend to slide. Okay. So to keep it from sliding, we have to apply some kind of force. In the seventh part of the question, they are saying that apply the force horizontally. What is the minimum amount of force we require? So horizontally means we are pushing it like this. We are applying an external horizontal force. So we have to find minimum magnitude of F so that the block does not slip for equilibrium condition. So it's a limiting friction problem. Okay. So just make the free body diagram. As usual, everything in Newton's laws is to do with free body diagram. So the forces, it's in ground frame only. I'm making the FBD. This is in inertial ground frame, and the body should be in equilibrium. So its acceleration should be 0. So forces acting are the external force we are applying, the gravitational force, mg, then normal reaction, and finally friction. Now since we are applying minimum amount of force, the tendency is to slip down the inclined plane. So friction will have to act up the inclined plane. So this will have to be static friction. And as I said, since we are talking about minimum force F, so friction is preventing the slipping along the direction of mg sine theta. So for this condition, mg sine theta is greater than f cos theta. So tendency for slipping is down the incline. Hence friction is acting like this. Okay. So now for equilibrium, our condition becomes that static friction plus f cos theta together balance mg sine theta, because f cos theta is smaller than mg sine theta. So you can see that friction needs to act in this direction. So this is our first equation, and of course normal reaction is coming as the sum of these two now. Now limiting condition is that static friction cannot exceed mu m. So substitute from the first equation static friction on the left hand side, that is mg sine theta minus f cos theta. So this should be less than equal to mu into n on the other side. So n is coming from the second equation, which is f sin theta plus mg cos theta. So this will give us a limiting condition. Keep mg on one side, so we have sin theta minus mu cos theta, and keep f on the other side, we have cos theta plus mu sin theta. Okay, so you're finding the condition on f. You can see that f should be greater than equal to this term. This. Okay. So from this only you get your limiting condition. So the minimum amount of force you have to apply, from this you can see, is mg this becomes your answer. Now just substitute the values. So I think mass of the block should also have been given 2 kg block. Substitute m as 2 kg, theta as 30 degrees, mu as 0.2, and you will get the answer. Okay. So hope this is clear, people. Just go through this question. We will discuss the next one after this. Okay, now Krishnan, you have asked the first and second question. Both are based on the same concept, so I'm just explaining them on the side over here. Maybe you have not understood what the question is saying, so I will just explain it quickly to you. So both first and second, you have to use this concept that a block is on a rough horizontal surface, and it is moving on the surface given some kind of initial velocity. So if this surface has coefficient of friction mu, and this is moving with an initial velocity of u at t equal to 0. Now what will happen is immediately friction, kinetic friction like this will start acting. So that kinetic friction will be mu n, which will be mu mg. So that will create a rate of deceleration for the block. So this A, you can see, so the rate of deceleration will be mu g. Okay. So as a function of time, your V will be u minus at, and your S will be ut minus half at square, and your V square will be equal to u square minus 2as, where A is mu g. So these are the equations you need to solve both the first and second question. Okay, Shikhar, I will give you the acceleration in the first case also. I mean in 6a also. Okay. But just note this down first. So Krishna, no, first and second question are clear to all of to you. Okay. Austin, I have received your doubts also. We will discuss question 14 and 26. Okay. So we will quickly discuss 6a also after this, but in general, I'm going to move to question number 10 and 14 after this. Okay, so start going through those questions. If you finish noting this down, start going through these questions. Okay, Anna, I have received your doubts also. So we will discuss 13 also. Okay. So hope you understood question number 7. If you finish writing down, please start going through question number 10 and 13. We'll discuss those two next. Yeah, Durgesh, the condition we are taking f cos theta is less than mg sin theta is because we are finding the minimum value of f. We want to apply the minimum force, na? So it should not be such that it's becoming f cos theta is becoming larger than mg sin theta, because then the tendency is to slip up the inclined plane. We're trying to prevent the tendency to slip down the inclined plane. Okay. Yeah, Prachi, I've received your message also. Question 31, I will be coming to it. 7th, you're not getting the answer. Okay, let's calculate. See, one thing you can do to make the calculation easier, no? When you're calculating this f minimum, just divide the numerator denominator by cos theta. That's a trick you can use. So this becomes tan theta minus mu upon 1 plus mu tan theta. Okay. Now your tan theta here is tan 30 degrees, which is 1 by root 3, okay, which you can write as root 3 by 3. So that is approximately 1.73 divided by 3. So that is approximately 0.64. Okay. And I think you have to take G as 9.8. I'm not sure. Is it given 9.8 or 10? Nothing is given. So let's take it as 9.8. So 2 multiplied by 9.8 into 0.64 minus zero point 0.2 upon 1 plus 0.2 into 0.64. This calculation. So that is becoming 19.6 multiplied by 0.44 divided by, ये कितना हो जाएगा 0.128. So 1.128. Yeah. So this calculation, let us do it. So I'm getting this 7.64, actually 65. newtons. This is what I'm getting the F minimum. So you might have made some calculation mistakes, Samarth. Let's check it out. And in general, like, I trust that you people should be able to do the calculations by yourself. So you're getting the same thing. Oh, wait. We don't have to find the. This is a different situation. We have to find the minimum amount of force required to push the block up the inclined plane. This is the equilibrium condition. Okay. This is different. Okay. That's why our answer is not matching. This is correct for equilibrium, but in this thing, in 7th question, they have asked to repeat part A. So in part A, what we have to do is we have to find the minimum force. This would have been for part B, but for part A, we have to find the minimum force for it to slide up the inclined plane. Okay. So if it is sliding up the inclined plane, we have to actually overcome the friction. So to make the block slide up the inclined plane. Now that's a slightly different situation. Still want to apply the force horizontally, but in such a way that now the block has a tendency to move like this. It's just about starting to slide, so acceleration is tending to 0 but is sliding up. So in this case, what will happen is you can see the friction will be acting, so we need much larger amount of force. Okay, because if the block is moving like this, then there will be kinetic friction acting like this. Okay. Okay. So our proper free body diagram, that will be looking like this now. F is like this, normal reaction is like this, mg is like this, but the friction is down the inclined plane. Okay. Because the block is tending to move like this. Its acceleration is tending to 0, just about starting to move, but like this. So this is theta, and mgf normal reaction and kinetic friction reacting like this. Okay. So this is in inertial frame, of course. Okay. So we will have f cos theta minus mg sin theta minus kinetic friction is equal to ma, and normal reaction is equal to mg cos theta plus f sin theta. So we'll be able to use those earlier equations only, but we'll see that. Okay. Now the condition for it to start slipping is that the acceleration is greater than equal to 0. So our limiting condition here becomes like this. So for motion up the incline, we should not be getting a as a negative quantity, we should be getting a as greater than 0. So we should be getting f cos theta minus mg sin theta minus kinetic friction as greater than 0. So f cos theta has to exceed mg sin theta plus kinetic friction. Now we put kinetic friction as mu n, okay, from here. So this equation will now convert to this, that f cos theta is greater than mg sin theta plus mu into f sin theta plus mg cos theta, like this. Okay, so you will get f is greater than this kind of thing, mg into sin theta plus mu cos theta upon cos theta minus mu sin theta. That trick I was telling you yesterday, na, that when you reverse the direction of friction, you can just replace mu with a minus sign. So if you compare this with the above result we got, na, just replace mu with minus mu. You'll see you get the same thing. Okay. So finally, this is the thing. Okay. So the minimum amount of force is just about equal to, because it has to be greater than this. Just divide numerator and denominator by cos theta, that trick. So tan theta plus mu upon 1 minus mu tan theta. Now you do this calculation. So this will be 2 into 9.8 into so 19.6 into 0.84 divided by 1 minus. So do this calculation, you will get the answer. Okay. Whereas the above case would have been, if we are preventing it from sliding down the inclined plane, the minimum force we have to apply. This is a different case. You have to prevent it, you have to make it slide up the inclined plane. So this is the minimum force for it to slide up the incline. Yeah, so thanks for pointing that out, Samant, because I had taken the language of the question wrong earlier. Okay. The condition is different. We wanted to slide up the incline, not down the incline. Okay. Now, Shikhar, similarly in the 6a question part, देखो यहाँ पे उसको we are making it slide up the inclined plane ना, तो कोई upper limit नहीं है. But if we were keeping it at rest, then this would have been the maximum. Understand the point? If we are keeping the object at rest, then the acceleration is 0 in this case. So this condition that we have written, na, that acceleration greater than 0, this is for slipping. But acceleration equal to 0 is for not slipping. But that would have given the maximum force for no slipping condition. And the above was the minimum force for no slipping. So that minimum to maximum is like the range of force for no slipping. तो यहाँ पे क्या हो रहा है, ये force 17.5 पे actually the block will be at rest. It has to be slightly greater. That's why I've written approximately equal to 17.5, because it has to be greater than this for it to slip. If it is equal to this, it is the maximum force for no slipping condition. You understood this point? Okay, Shikhar. Okay. So if, for example, I ask you what is the range of horizontal force so that it does not slip, then that range is from 1 minimum to 1 maximum. Now the minimum is the one we calculated above, that 7.6 or whatever we were getting, and the maximum is this one. Minimum से कम होगा, it will slip down the incline. Maximum से ज़्यादा होगा तो it will slip up the incline. Okay. Now similarly in question 6a part, the thing is the same. You are wanting to make it slide up the inclined plane, but you are applying the force parallel to the inclined plane. That is the difference. Okay. So to just modify your free body diagram, and becomes a simpler thing, okay, because you don't have to resolve F and it doesn't affect your normal reaction. You want to apply the force in such a way that it will tend to slip up the inclined plane. Just a minute. Yeah. So here you want to apply the force parallel to the inclined plane so that it starts slipping. So acceleration tending to slip. here f should be greater than mg sine theta plus mu n. So that condition is actually the same as this, if you see. Only this f cos theta and this f, and n is equal to mg cos theta. So f should be greater than mg sine theta plus mu mg cos theta. This should be the condition for a to be greater than 0. Okay, so good. I think all of you understood this. Samar, this is clear to you also? Okay. Now let us move on to question number 10. So 10 is about that angle of friction. So on a horizontal surface, we're having some kind of a block. Okay. Now notice nothing else is given. Whether we are applying some external force horizontally or not, or whatever, just coefficient of friction is given. Not even the mass of the block is given. Okay. But we have to find the maximum possible angle between normal reaction and the net contact force. So let's say normal reaction is acting like, obviously normal reaction is acting like this, but let's say the block is moving like this. We don't know with acceleration, without acceleration, or what. So we also know that friction will be acting like this. Okay. So this friction, it could be static because it's not exactly given that the block is in motion. So static friction is less than equal to mu1. Okay, could be kinetic. It could be in motion also. So kinetic friction is equal to mu n, since only one value of mu is given. Yeah. So now the net contact force, okay, that is basically the resultant of the two contact forces, normal reaction and friction. So that resultant is actually like this. It is square root of n square plus f square. It is a vector sum of these two. So now whether or not the object is moving, whether or not it is static or kinetic friction, always normal reaction and friction will be perpendicular to each other. That is one guarantee we have, because by definition normal is normal to the surface of contact and friction always acts tangentially to the surface of contact. So we know as a fact that these two forces are perpendicular to each other. So that's why the net resultant force is this one. And this is the angle they've called lambda. Lambda is the angle of the resultant contact force, okay, with respect to normal reaction. What angle it is making with respect to normal reaction, vector n. So as you can see in this diagram, that lambda is equal to how much? Tan lambda is f by n, or you can also say that cos lambda is n by r, or sin lambda. It all depends on how we want to express it, but how it is given in the question, we want to express it in terms of tan, so we'll use this expression. Okay, so lambda is equal to tan inverse f by n. Now since we don't know what type of friction it is, we have to use this whole thing. So here what it's saying, friction could be anything from 0 to mu1. So that means lambda could be anything from tan inverse 0 to tan inverse mu. Okay. So this is telling that lambda's maximum value is tan inverse mu. Okay, so this is the meaning of the 10th question. Okay, so just go through this once carefully. Okay, next we will move on to 13th question. 13th, 14th, 18th. Okay. Okay, so 13th, I'm just quickly going to make the free body diagrams. So that's all you need. Let's say this is A, this is B, and this is C. So now the things that are given to us, this coefficient of friction on this surface is 0.2. Okay. And mass of A is equal to 15 kg, mass of B is equal to 5 kg, okay, and mass of C is equal to 5 kg. Okay. So to be able to find the tension in the two strings, which is what they are asking, if this tension is T1 and this tension is T2, so obviously T1 is greater than T2. That too we can see because that block is heavier. But what we don't know is whether the block is going to slide or not. Okay. So you have to see, you have to first of all determine if the system has enough friction for equilibrium. This thing is important. We need to find out whether the acceleration is zero or not. Okay. So in most problems of friction, if there's a question mark on whether the system is in equilibrium or not, okay, or whether the object is slipping or not, you always start with the assumption of no slipping and justify the assumption. So no slipping condition अगर है, अगर acceleration zero है, so from A's free body diagram you can see that T1 has to be equal to ma into g. From B's free body diagram you have to see that T2 has to be mb into g. So now you come to from C's free body diagram. see that this has to be mc into g. Okay, now you come to B's condition, and B's condition you'll understand that this T1 will now become 15g. This will be 5g. Its own weight is 5g. So normal reaction is that much. Now it has a tendency of slipping like this, so static friction has to act like this. So how much the static friction has to be equal to? Static friction has to be equal to T1 minus T2, which has to be 15 minus 5 or 10g. Now obviously that much is not available to you because इसका weight ही तो 5g है and coefficient of friction is less than 1 obviously. So this you can see is not possible because maximum friction is mu n, which is 0.2 into 5g. So this much friction is not possible for us. So that means this condition is not possible. Equilibrium condition is not possible. So the moment we know equilibrium is not happening, that means what is occurring. Therefore, the system has slipping for block B towards the left. Block A will be coming down, block C will be going up with some common acceleration. So now you have to just solve for that condition. The rest of the things is done. Okay. This is coming down with acceleration, this is going towards the left with acceleration, this is going up with acceleration, and on this there is kinetic friction of mu n acting. Okay. Okay. So now your equations will become like this. For A, you will have 15g minus T1 is 15a. For B, we will have T1 minus T2 minus mu into 5g, because this kinetic friction will be mu into 5g. That is equal to 5a. And for C, we will have T2 minus 5g is equal to 5a. And now just solve these equations, you will get the answer. Okay. Yeah, so a couple of you have asked this question. I think Anna is one of the people you asked. Hope this question is clear now. Okay, so 13th is done. Let's move on to 14th. So coefficient of friction between the road and the tires of a vehicle is 4/3. Find the maximum incline the road may have so that once hard brakes are applied, vehicle going down at 36 kilometers per hour is stopped in 5 meters. Okay. So its initial velocity is 36 kmph, that is the same thing as 36 into 5 by 18, so that is 10 meters per second. Now you apply the brakes, so the tire starts skidding. So when the tire starts skidding, there is kinetic friction acting on it, which is mu n. Okay. So this vehicle, it should have a deceleration. Deceleration is such that by the time it comes to rest, it has covered a displacement of, how much is it? 5 meters. Okay. So your kinematics will tell you that v square in the case of deceleration is like this. So 0 should be equal to 10 square minus 2a into 5. So we want a deceleration of 10 meters per second square. So for this deceleration, we have to find out how much theta is. So free body diagram as usual. Okay. Mu n, and let's resolve mg. So mg sin theta, mg cos theta, and we want कि ये deceleration कितना होना चाहिए? ये deceleration 10 होना चाहिए. Okay. So mu n minus mg sin theta should be equal to ma, and n is of course equal to mg cos theta. That's our second equation. So you'll get a as mu cos theta minus sin theta whole thing into g. Okay, and that should be 10. So 9.8 into 4 by 3 cos theta minus sin theta should be equal to 10. So this is the equation you have to solve. 4 by 3 cos theta minus sin theta. I think we have to take g as 10 in this, or no? So this is okay. I'll just give you a hint on how to solve this type of equation trigonometrically. So whenever we have an equation like this, we have some, a linear equation in sine and cos. Okay. So ABC could be any three constants. So one of them could be negative also, like here. So what you do is, you on the left hand side, you multiply divide by root of a square plus b square. You know this trick in trigonometry, right? Okay. So the left hand side then becomes root of a square plus b square into sine of theta plus something. Okay. Where that alpha becomes tan inverse of b by a, and then you solve. So apply that method over here. Rolling friction, Prachi, is not in this chapter. Rolling friction comes much later. It is 3 chapters afterwards. After work energy, center of mass, then there is a topic called rotational mechanics. In that, rolling friction will come. यहाँ पे rolling friction नहीं बोला है. यहाँ पे the brakes are jammed, so the wheels are skidding. So it is kinetic friction. Yes, Krishnan, whenever you have an equation where you have a linear term in sine and cos, linear term means like this: a sine theta plus b cos theta kind of thing, where a and b are constants, you have to use this method. Okay, so hope this is clear now. Right, now next, what are we going to do? Question number 18 and 19 you have asked. Now 19 is very similar to the question we discussed yesterday. Okay. So 19th is very similar to the question we discussed yesterday. 18th is also something like that only. But so I'll give you the basic idea for 18th and 19th. Okay, finish writing this down first. Okay. Now in 18th one, we are keeping the two blocks directly in contact. Like this. Let's say this is A and this is B. And in 19th one, there is a light rod. Now light rod makes things a little bit different compared to a thread, because we had discussed about a thread yesterday. So light rod में क्या होता है ना, both push and pull is possible. So light rod means no matter what happens, they will be moving together. Whereas yesterday we had seen the question that there was a thread joining A and B. So thread के case में क्या हो रहा है ना, that it is not possible for the thread to push the blocks. It's only possible for it to pull the blocks. So only when A has a tendency to move faster, there will be tension in the thread. But this time, this is a light rod. Okay. So here it's very simple. In this case, what happens if coefficient of friction of A is greater than coefficient of friction of B? Okay, then B tends to accelerate faster. So because it tends to accelerate faster, it will push A. Okay. So acceleration of A will become equal to acceleration of B, and there will be some kind of contact force between them. So this will experience a contact force like this will experience a contact force like this, and they will have common acceleration. Okay. Whereas on the other hand, if mu A is less than mu B, okay, then A will accelerate faster. So eventually they would have lost contact. Acceleration of A will become greater than acceleration of B, and there won't be any contact between them. Okay. Something similar will happen if they have equal coefficient of friction also, but only they will remain visually in contact, but there won't be any normal contact force. So here also acceleration of A will become equal to acceleration of B, equal to G into sine theta minus mu cos theta, the common value of mu. But normal reaction will be zero, because both have the same tendency of acceleration. They have common acceleration, but there is no normal contact force between them. This will be the case. So these are the three types of cases which are possible in this. Okay. Whereas in this one, what is happening? This one, because it's a light rod, so that's why A and B always move together. The difference is that if mu A is greater than mu B, then B tends to push against the rod. Okay. So as they are moving, B will tend to push against the rod, so the rod will push back. So the direction of tension in the rod will be like this. Okay. On the other hand, if mu A is less than mu B, then A will tend to pull. Okay. So at that point of time, A is tending to pull on the rod. So the rod will have to pull back. The rod has a tendency to stretch. Here the rod has a tendency to get squashed. So the rod will apply inverse tension like this, but they will have common acceleration. Okay. And if mu A is equal to mu B, then acceleration will be this, okay, and tension will be zero. So these are the different kind of cases possible. I mean, day before yesterday, and whenever we had the last physics class of Blue House, the fifth session of friction, we had discussed about this. Okay, so that's done. Now let's come to question 21. Oh, question 20 also. Yeah, we'll discuss 20 also. 20 is a very interesting problem actually. It's more of a maxima minima kind of problem. So we have this block of mass m, so resting on a rough surface which has coefficient of friction mu. Now it's asking what is the minimum force we need to disturb it from the equilibrium, that is to make the block move, and in what direction we should apply the force. So you just assume that we are applying some force at some angle theta to the horizontal, suppose. Okay. And this just about starts to move, so its acceleration is tending to zero. So now we look at the free body diagram. So we have this force, we have vertical normal reaction, we'll have vertically downwards weight, and it's just started to move, so we'll have kinetic friction. This angle is theta. This acceleration is just about tending to zero. So we have F cos theta has to be just about balancing mu n, or kinetic friction. Okay. And we have n plus F sin theta is equal to mg. So from equation 1 and 2, you get F cos theta is approximately equal to mu into mg minus F sin theta. So from this you can see F is equal to how much? It is mu mg upon that kind of linear relation. This relation. So this is f as a function of theta. Okay. This is where your mathematical analysis comes in now. So this is the force as a function of theta. Now we want to find the minimum value of force, and for what theta f is minimum. Okay. So one is we can use maxima minima. We can take df by d theta, that is f prime theta equal to 0, and second derivative, that is f double prime theta, should be, we want minima, so it should be positive. Okay. But that's very lengthy. We can also use trigonometry. Let's see how we can use trig. So here you can see this f is actually mu mg divided by some linear function of theta. Say that. Yeah. So f minimum will be mu mg upon this function's maximum. That's going to be much easier. So let's analyze this. So this denominator function is mu sine theta plus cos theta. Now we want to find this function's maximum. Okay. So that is very easy because the trick I just told you, you can write this as this. Okay. So you can see that this function's maxima is square root of 1 plus mu square, and it is for sine of theta plus alpha to be 90, I mean to be 1. So that means it is for theta plus alpha to be 90 degrees. So that condition is that theta should be 90 minus alpha. And what is alpha? It is tan inverse of this by this, 1 by mu. Okay. So theta should be tan inverse. Okay. As if we say that theta is 90 minus tan inverse 1 by mu. That means if we have a triangle where this is in the ratio mu is to 1. So this angle is alpha because tan alpha is 1 by 1. So this angle is theta because theta is, so this becomes 1. So again that trigonometry trick becomes very useful in a question like this. So I'll just minimize this a little. This is an important application of friction as well as trigonometry. Some of that is coming from this concept. Now see, we are solving this kind of linear equation, e sin theta plus b cos theta. इसको हम क्या कर रहे हैं, इसको हम ऐसे लिख रहे हैं, रूट ऑफ ए स्क्वायर प्लस बी स्क्वायर इंटू ए अपॉन रूट ऑफ ए स्क्वायर प्लस बी स्क्वायर sine theta plus b upon cos theta. Next step we are writing cos alpha sine theta plus sine alpha cos theta. So this is becoming root of a square plus b square into sine of theta plus alpha. But there you can see where sine alpha is b upon root of a square plus b square. Cos alpha is a upon this. So in other words, tan alpha is b by a. So alpha is tan inverse b by a. So this concept only we are applying here. But only thing is over there, our a is 1, sorry, a is mu and b is 1. Okay, so this is becoming 1 by mu. So this is something you have to remember as a method. If you take time to derive this whole thing, you will not be able to solve this in the time frame of the exam. You can sit and do it at home, but in the exam time frame, this thing has to be set in your mind. This whole, basically, this thing has to be directly converted to this, where you know that alpha's value is this. This should be absolutely set in your mind. Yeah. So hope this question is clear, Shikhar. Next up, we will do 21, 23, and 26. Okay, 25 also. Fine, we'll do. And 24 also. Okay. Okay, so quickly, 21 is mostly about getting the free body diagram. So man is pulling down on this rope, which is connected by this whole arrangement of pulleys. Like this. So if the man applies some downward force, that becomes the tension in the rope. So that tension is this has a coefficient of friction mu. So first of all, whatever force the person applies, that becomes a tension in the rope. Okay, we'll discuss. Okay. So make the man's free body diagram. So on the person, this mg is some kind of normal reaction the platform is applying in this tension. Okay, and he's in equilibrium. Then you make the platform's free body diagram. Now from the platform's free body diagram only we'll get the limiting friction condition. So the man is pushing it down with some normal reaction which is not equal to weight, that is mg minus t. Okay. There is its own weight, small mg. Let's say there is this normal reaction which is n prime. Okay. And there's also this horizontal tension T, and we want this to be in equilibrium, so this has to be balanced with static friction. So we have n prime is small mg plus n. This is our second equation. So when you substitute this here, this becomes n prime is equal to mg plus capital Mg minus t. Okay, so it's not the sum of the weights, and T has to be balanced with static friction. That's our second equation. Third equation. Now static friction cannot exceed mu n prime. This is our limiting condition. So static friction should be equal to tension from here, and normal reaction from here is this. Okay. So as you can see, we will get there, and this T only is equal to F. So this is the same condition on F. So ultimately, it is all about not making any mistake with free body diagram. If you're clear with FBD, Okay, so let's move on to question 23. So I will be doing one part of question 23. Okay, and you'll use the same method. So I'll try to pick up the part which is more tricky. So let's do the third part where you're applying the force on the 7 kg block. Just a minute, guys. I'll reload the software once. Yeah, so I'm going to start the 23rd question. Let's come to that. So I'm going to do one part of the question where we are applying the force on the lowest block. So on the smooth horizontal ground, we have the 7 kg block, then the 3 kg block, then the 2 kg block finally. So I'll just label them like this. This is a smooth surface, whereas this has coefficient of friction 0. 0.2 and this has coefficient of friction 0.3. So one thing you can do before starting the question is understand the limiting frictions. So if you see M1's free body diagram, you can see the normal reaction here is like this. So any friction that acts on this surface, for example, if it acts like this friction is less than equal to mu1 n1. So that means this friction should be less than equal to zero point 0.2 into 2g, or F1 should be less than equal to 0.4g. I think we have to take G as 10 or 4 newtons. Similarly, if you now see M2's free body diagram, so there is this normal reaction N1 acting like this. There is its own weight and there's normal reaction N2 acting like this. So if there's friction here, N2 is equal to N1 plus M2G, so it is a combined weight. So this normal reaction is how much? It is 50 newtons. Okay. So this friction is less than equal to mu 2 N2. That means this friction is less than equal to zero point 0.3 into 50, so 15 newtons. So these are two important values that you should have beforehand. Always helps if you have these values written out. This and this. Okay, now we are applying some force. What is it? 10 newtons. So F equal to 10 newtons. We have to find out the accelerations. So now what you do is you always start by assuming no slipping. So assuming no slipping at both contact surfaces, that is between M1 M2 and okay, so E1 is equal to A2 is equal to A3 is equal to A, suppose. Okay. So make a combined FBD. So this combined block which has no friction on the ground, this will be moving with this acceleration A, and the mass of this combined block is okay. So with this assumption, the acceleration should be F upon this combined mass. So it should be 10 upon 12, 5 by 6 or is acceleration. Okay. But we have to check friction needed. Okay. So for checking friction needed, that is where your individual free body diagrams come in. Okay. So that's where your understanding comes in, that when you apply an external force like this is tending to slip forward. So on this block, this friction will act backwards. On this block, this friction will act forwards. That is tending to make this slip forward. So on this, there is friction acting like this. On this, there is friction acting like this. So this is very important to understand. Tendency for slipping, say friction का direction. How we understand कि अगर friction नहीं होता, then this block would have slipped forward. So it would have slipped towards the right. So on it, friction has to act towards the left. So this friction acting on the middle block M2 is the reaction for the friction acting on the lower block M3. So this and this have to be in opposite direction. Okay, similarly for the other pair. So now you understand, you start by taking M1's free body diagram. So on M1, there has to be just one horizontal force of F1 acting like this, which is giving it this acceleration which we have calculated, 5 by 6. So F1 needs to be how much? M1A. So M1 was 2 kgs. Okay. So 5 by 3 or 2.67 newtons. Now see, is that available to us? Yes, because we have seen above that F1 is less than equal to 4 newtons. So maximum value we have is up to 4 newtons. So 2.67 is very possible. So that means there is enough friction between M1 and M2 to prevent slipping. Okay. But also check on the other one. So for that you can take the free body diagram of M2. On M2 we know that there will be this friction acting backwards. and we just calculated this one will, okay. This is a static friction, because there's no slipping between M1 and M2, but how much it is 5 by 3 newtons. So now we need to find out how much this needs to be, because this also needs to move at the acceleration of 5 by 6. So F2 minus F1 should be equal to M2. So F2 minus 5 by 6 should be equal to M2 is 3 kg into this common acceleration was 5 by 6. So F2 needs to be 5 by 3 plus 5 by 2. So the amount of friction needed here, (25 by 6), something like this. Now again, this is possible for us because we had seen the maximum friction is up to 15 newtons. So F2's maximum value available to us was up to 15 newtons. So this is also possible. So there is enough friction between M2 and M3 also. Okay. So therefore the assumption is correct. A1 will be equal to A2 will be equal to A3, and that one will be equal to 5 by 6 or this much. Okay. So just go through this whole method once. So this is the same method we always apply for questions where there are 2 or 3 blocks or whatever. Yeah, limiting condition has to be found out. Yeah, both 2 and 3 block problems, same method. You always start with the assumption of common acceleration, find out that common acceleration, then substitute that in the individual free body diagrams and check for the friction required. Okay, now 24th and 25th both have the same type of situation. So this is small m, this is capital M, and there is friction mu here, whereas this is a smooth surface. Now we start pulling on this block with some force F. So we have to find the maximum force so that there is no slipping. Yeah, Saman, so I've done many questions on 2 and 3 block problems. You know what to do when the assumption of no slipping is not true. Then there is A1 will not be equal to A2 and there will be kinetic friction acting between them. Or if there is slipping between the other two blocks, then A2 will not be equal to A3 and the friction will be kinetic. So you make your free body diagrams again with different acceleration and the friction is kinetic friction. So you know its value. Even day before yesterday, we discussed couple of problems based on this. So you have discussed many. So you have to just go through those problems again, and you have to work out some questions yourself also. Okay, so here, the moment you apply this force like this, it creates a tension in the thread, which also acts on this. Okay. So now again, you need to understand कि if there was no friction, so क्या होता है? This would have slipped towards the left. So friction has to act on this like this, and therefore on this like this, and we want that the system should be in equilibrium. So this is the case. And of course the vertical forces you can see, they're showing it separately because so यहाँ पे जो friction है, this will be less than equal to mu n. So mu small m. This is the limiting value. Okay. So for equilibrium we have this one, F should be equal to T plus static friction, and here we have T should be equal to static friction. So combine these two equations, so you can see that F has to be equal to 2 times the static friction. Now static friction is less than equal to mu n. So F by 2 should be less than equal to mu n. So the amount of force we are applying should be less than equal to 2 times mu n. So this is the solution and the answer for the 24th question. And 25th, what is happening? This whole situation is inside an elevator. This whole system is inside the elevator, which is accelerated in which direction? Upwards, which is coming down with an acceleration a less than g. So what that acceleration does is that, okay, I will discuss Baba. तो कर दो ना, डबल फोर्स कर दो, एक्सीलरेशन आ जाएगा दोनों का, just calculate acceleration. There's nothing difficult in that anyway. So in this, what will happen is this acceleration will affect the normal reaction. Now you see, for small m, there is mg, there is pseudo force, and there's normal reaction. Okay, so this normal reaction is becoming m into g minus a. So friction is becoming less than equal to mu n. ये हो जाएगा. Okay. So this thing, we just have to replace it like this. Okay. Okay. Now in this one only, if F is equal to double of this is your F max. That means it is 4 times mu mg. Okay. Then slipping will occur. So अगर slipping occur कर रहा है तो ये कैसे move करेगा? Like this. And the lower block will be moving like this. And just make the FPDs ना. इस पे kinetic friction act करेगा. So that is mu mg. इस पे tension, kinetic friction. So F minus T minus mu mg is ma, and T minus mu small mg is capital Ma. And just substitute the value of F in this. Okay. Substitute the value of F as 4 times mu mg and solve for A. What is difficult in this? It's a limiting condition which is the difficult thing. No? Once you got the limiting condition, the kinetic condition is very easy because it's just solving F is equal to ma. Okay, so hope this is clear. Okay, 27th, we'll discuss the free body diagrams. Because again, the question is completely based on application of free body diagram. Okay, so we have this situation. Now there are coefficient of friction between the two blocks is mu1. So this is mu1, and coefficient of friction between the block and the floor is mu2. Okay. So what will happen is this will tend to accelerate down, but this is the relative acceleration of small m with respect to capital M. Because remember, capital M is now going to start moving with acceleration a like this. So actually, the small block as it moves down this will also be moving down. So after some time, it will be here. So it will have an actual motion in this sort of direction. It will have an actual acceleration in this sort of direction. It will be the vector sum of this horizontal acceleration and this relative vertical acceleration, like this. Okay. Now the next thing you'll do here is you'll make the FBD of the block small m in the non-inertial frame of the wedge capital M. So on that block there is pseudo force, okay. There is tension in the string, there is its own weight. Pseudo force will generate a normal reaction, and because this is now slipping down, this is the relative acceleration in this non-inertial flow. Okay. So there will be kinetic friction acting here. So that kinetic friction will be equal to mu n. N will be equal to ma, and we have mg minus kinetic friction minus t is equal to m into a relative. That's this equation. Yeah. Then you will also have the constraint relation from thread length conservation. We'll have this. So this is going to be an important equation. And then finally we come to the free body diagram of the wedge in the ground frame. Now this is the one which is little tricky. Okay. So on the wedge there is a very large number of forces acting because there's a pulley attached here and there's also in contact with the block. So there's tension, one more horizontal tension here. Then the block is pushing it with a normal reaction here and also applying a downward kinetic friction equal to mu n on it. Okay. And of course, the block's own weight, capital Mg, normal reaction that the ground applies, n prime, let's say, and some kinetic friction here, which is mu2 into n prime. Okay. And all this together in the ground frame is giving it an acceleration E like this. This is an inertia. Okay. So just showing these forces like this, there's a horizontal tension of T plus T 2T, vertically downward tension of T. Then there is the interaction with the smaller block, which is this normal reaction and this mu n. I have taken mu, just replace it with mu 1 later. Okay, what I have taken as mu, you replace it as mu 1. Okay. There are these two forces. Okay. Then there is, of course, the block's own weight, capital Mg, the normal reaction with the ground n prime. Okay. and the kinetic friction that the ground is applying, which is mu to n prime, and this is horizontal acceleration. Okay. First of all, you need to understand that n prime is equal to t plus capital Mg plus mu n. So that's your third equation. Okay. And 2t minus n minus mu to n prime is equal to capital N. So that's your fourth equation. So the equation solving is also quite complex in this. Okay. So now, if you look at the whole set of equations that you have, you see that you have your variables are n, n prime, t, a relative, and a. So these are your variables, five variables. Okay. So you need five equations. So this one will act like your fifth equation. So four equations you are getting from dynamics, and one fifth equation you are getting from this. Okay. Four equations from F is equal to ma type equations, and one constraint relation. This is the constraint relation. Okay, so just make a note of this also. Yeah, I'll share the notes and recording today itself. Don't worry. I'll send you the notes now. So now, just in the time remaining, I will do one more question. Question 31. The other in between questions are relatively easier, so you should be able to manage yourself after going through these questions. 31 is also, it's not a difficult question, but you just need to understand how to apply one additional concept in it, and that is the concept of relative motion. So what is happening in this question is that the ground has a coefficient of friction of mu, and between these two there's a coefficient of friction which is half of that, mu by 2. And what we are doing is at t equal to 0, we have applied some sharp impulse. That means some impact force kind of thing has been applied, such that both the blocks start moving together with a velocity of V naught at t equal to 0. V or V naught, whatever. Okay. So you have to find after how much time they will lose contact. So what you have to understand here is that the moment you have given this a motion like this, the lower block will start experiencing friction because it's moving like this. So it will experience friction, let's say F1, which is kinetic, slipping on the ground. And that will be equal to how much? Mu into M plus mg. Okay. So क्या होगा? That will give this a tendency of decelerating. So that means in comparison to the upper block, it has a tendency of moving backwards. So now the upper block is also moving at the same speed v initially. Na? So this has a tendency to continue, but this is getting decelerated. So the friction between them will act in such a way that it acts forward on this and backwards on this. And this friction will be equal to mu by 2 small m. So this is how the free body diagram of small m and capital M respectively are looking, both in inertial frame. Okay. So as you can see, this will have some deceleration E1 and this will have some deceleration E2, and we can find those decelerations. E1 will be nothing but F1 by small m, so that is mu by 2g, and for this one we'll have the equation, sorry, F, let's write this as F2. So इसके लिए equation क्या हो जाएगा? F2 minus F1 is equal to capital M into its deceleration A. So mu m plus m g minus mu by 2 mg is capital M2. So E2 you can see we will get as mu into m by 2 because this and this, okay, plus capital M into g by capital M. Or we can write E2 as mu into 1 plus m by 2m g like this. Okay. See, this is your E2, this is your E1. Now once you got E2 and E1, what you do is you use relative motion. So you look at as if you are standing on this and you are looking at the motion of this. So you will see that with respect to you, this will have a relative acceleration in this direction. Because if you take this as your x-axis and this as your y-axis, the acceleration of block 1 was minus mu by 2g I cap. The acceleration of block 2 was minus mu into 1 plus m by 2m g I cap. So the acceleration of block 1 with respect to block 2, that will be this minus this. So when you work this out, this will come out to be a positive quantity, and it will come out to be mu by 2g into 1 plus m by n. This kind of term you will get. Okay. So this is your relative acceleration. Okay. Now at t equal to 0, your relative velocity will be 0, because again your initial velocity of block 1 was v naught I cap. Your initial velocity of block 2 was also v naught I cap. So initial relative velocity of 1 with respect to 2, this is 0. So to this guy, this is what it is looking like. So at some time it will reach here. That's when it's going to. So this displacement, relative displacement, should be equal to the length. Okay. So this is the motion of the block small m relative to the wedge or the platform, whatever. That's what we are looking in this part. Okay. So half AR into T square should be equal to L. So the time taken is square root of 2L upon the relative acceleration. So this is what we wanted to solve when we substitute relative acceleration. So that is how you'll get the time taken before the smaller block separates from the bigger block. Okay. In ground frame, actually, what will be happening is that both the blocks set off. If you are seeing with respect to ground, both of them have a common velocity of v naught here like this. Okay, and after some time, so this is the situation at t equal to 0. So after some time, this is what is happening. We'll have some different velocities. So v1 will be equal to v naught minus a1t. v2 will be equal to v naught minus e2t, like that. And this block's displacement s1 will be equal to v naught t minus half a1 t square. This block's displacement will be equal to v naught t minus half e2 t square. Okay. And the relative displacement s1 minus s2, that will be equal to the length. So that's another way you can solve it. But that will give you the same result as this. But it's easier to solve this in the relative motion frame, where this becomes square root of 2L by A relative. Now you substitute the value of A relative. Just the magnitude of A relative that you have to substitute. Substitute this here. Okay, people. So with that, we end today's session. And this is an important question, the last one in particular. So make sure you go through this. Okay, I will send you the notes and the recording as soon as possible. Notes I'll send just now. Recording in a bit of time. So all the best for tomorrow's test. Make sure you revise the last few questions we've done today and in previous lecture.